So today I'll be talking about a project on estimating the false discovery rate for a general model selection algorithm. So to begin, to motivate the talk, so here are my collaborators, Li Lei, formerly at Berkeley, now Stanford GSB, and Yishang Luo, who's still at Berkeley. So I'll start by trying to give you all a motivational challenge of visual multiple testing. So I'm going to show you a plot, and then your job will be to find the non-null. So this is a stylized scenario. Assume that we have 100 variables, and for each variable we have a z-statistic. And the z-statistics, they all have their own means, and they all have marginal variance 1. But they have some correlations with each other. And so in particular, there are 10 blocks of 10 variables each, and the blocks are independent of each other, but within each block, we have equicorrelations between the z-statistics. So in the plot I'll show you, the equicorrelations are 0.8, but you could imagine maybe this comes from some kind of batch effect, or if we have, say, a control, if we have different blocks and we have a control in each block and we're making comparisons to the control for that block, then we would have a 0.5 correlation between different variables in the same block. So you can imagine various stories for how we would get a data set like this, but I just want you to take it for granted. We have Gaussian data with this correlation structure. So the goal, 5 of these mu j values are non-zero, the rest are 0. And so the goal is to look at the data and find the 5 values that are non-zero. So just to, again, say with this plot, so within each plot I have 10 dots. I'm plotting the variable index, the horizontal axis here, and then this is. So each shaded band has one block of 10 variables whose z-statistics are correlated with each other. So the question is, where are the non-nulls? This is not a trivial multiple testing problem. One thing you might notice, if you look at the distribution of the z-statistic, only one of the z-statistics is larger than 2. So even if we made no correction for multiplicity whatsoever, we would only get 1 rejection. And certainly the B8 procedure at any reasonable level is not making any rejections here. But I would contend that if you stare at this, and I'll give you a minute, if you stare at this for long enough, you might be able to find some of the non-nulls, just visually. So I'll just give you a minute. So does anyone have a guess for where one of these non-nulls might be? Second block at the top. Okay, that's a good guess. What's that? Yeah. So what's special? What about the second block at the top makes you more confident about it than, say, the one that has a bigger z-statistic? Yeah, so it's standing out from its block. That's exactly the right thought to have. And if you apply this looking across the blocks, you might be able to see a few other places where we have one variable standing out. So in fact, these are the 5. These are the 5 non-zero. Okay, but pH didn't found, but Ting found. Ting was able to find them. So what does Ting know that BH does not know? Well, it's that the correlation is actually helping us here. So, but just looking at the z-statistic, or just looking at the z-statistics themselves, doesn't seem to be giving us the right answer. But since I told you that mu is sparse, you might think you could use a method like the lasso to try to find the non-nulls. So here, this is actually, if instead of mu, we had beta, and instead of z, we called it beta hat, this would be exactly the structure of a linear regression problem with a known error variance. Right? So we have some known correlation structure between the beta hats, and we probably wouldn't write it this way, but this would be exactly the lasso criterion for that problem. But anyway, or we could just directly say, well, okay, maybe we don't realize this is like a regression problem, but we still can write down the likelihood plus, plus some L1 penalty. And so what will we get? So if we start off taking no penalty, and then we gradually increase the penalty, and we'll get a sparser and sparser solution until at some point, we'll get exactly the right set of variables with no false discoveries. So the lasso actually is able to succeed in this problem. And the lasso is generally just doing a better job of classifying nulls from non-nulls because it's using the information that we just talked about. It's using this correlation. It's exploiting the correlation in the problem. But unfortunately, the cross-validated lasso with lambda selected by cross-validation doesn't actually do it for us. So here, in this case, we have 10 extra discoveries in addition to the 5 discoveries that we wanted. And that actually kind of makes sense. If we use cross-validation to select lambda, then we're not really then cross-validation is not really doing anything about type 1 error. It has no concept of type 1 error. It's just trying to do the best job in predicting, and adding a little bit of a noise variable just fundamentally doesn't interfere that much with getting good predictions. And the bias in estimating these 5 variables is at least as important. So cross-validation is not really doing the right thing here. Okay, so cross-validation gives us 10 false discoveries. And if we were to use the 1 standard error rule, we would get no discoveries at all in this case. We would choose the largest possible lambda. So instead, we could actually try to select lambda to target a false discovery rate. So in this example, I think in this example where you can see we're a little lucky that we happen to get all of these. But at least in this example, we can get perfect classification if we actually target the false discovery rate. So the goal for this talk is going to be to figure out how do we actually estimate the false discovery rate as a function of lambda. And what we're going to produce is a curve like this, this red curve to supplement the cross-validation curve. So again, here the cross-validation curve is giving us a fairly noisy estimate of prediction error, out-of-sample prediction error. But out-of-sample prediction error is not the same as type 1 error. And so we can supplement with this false discovery rate estimate, and maybe we use the false discovery rate estimate to select lambda, or maybe we would still use cross-validation to select lambda, and just use the false discovery rate estimate to have some sense of what the false discovery rate is. Now you can see this is actually quite noisy because we have high correlation between the different variables, but it still does a reasonable job of capturing the false discovery proportion, and even slightly better job of capturing the false discovery rate. So here we know the ground truth false discovery rate because we're simulating the data ourselves. And if we make the problem bigger, where we have 40 blocks instead of just 10 blocks, then we have smaller standard errors. We are still doing a pretty good job of capturing the false discovery rate here. But again, if we were just to look at the cross-validation curve, we would have no idea where this sort of transition happens, where we go from having very few false discoveries in the model to having mostly false discoveries. Okay, so the goal for this talk is really to figure out how do we construct this red curve. So we want an estimator, we'll call FPR hat, and it's going to be an estimator for a generic model selection method. We're not going to really assume much about how we're using, how we're doing model selection. So it'll work for a method like the lasso or graphical lasso, work for forward stepwise, Bayesian model selection algorithms, sort of marginal thresholding algorithms, what have you. Under standard hypothesis testing assumptions, so we're not really going to introduce new statistical assumptions beyond the statistical assumptions that we were already using to do single multiples, so single hypothesis testing. So here, maybe that means we're assuming a Gaussian linear model and we could use a t-test to do single hypothesis testing. Or if we had a Gaussian graphical model, we could also do t-tests to test for edges of the model. Or we could have a more general situation, so that we could be using something like conditional randomization test. If you're familiar with like model X knockoffs, or something like that. But we have some kind of standard way of being able to test a single hypothesis, and we're not introducing statistical assumptions beyond that. So in this for a general selection method under fairly standard hypothesis testing assumptions, we want an estimator that has provably conservative bias. So we'll be able to show that the estimator that I'll talk about will have an expectation which is never smaller than the expectation of the true false discovery rate. Okay, so the use cases of this that we envision. So we might just have a pre-specified estimator. So maybe we're just going to use lasso with some kind of automatically selected lambda, either maybe a fixed lambda or lambda selected automatically by cross-validation. And maybe we just want to assess what is the false discovery rate of that estimator before we go in and start interpreting the signs of the estimated variables. Or maybe we want to do some kind of trade-off of false discovery rate against cross-validated error. So, in a setting like this, we look at the cross-validation curve, and maybe it's fairly, maybe we really care about the share, so we might be tempted to use this lambda. But if we look at the right curve as well, then we might say, well, maybe we should choose a cross-validation. Maybe we should choose a smaller model that has a small false discovery rate and whose cross-validation error is not that much larger. So we could sort of informally trade off false discovery rate against the cross-validation error. Or we could actually tune the method to target a particular FDR that we have in mind. Depends on the goals of the analysis. Just one thing I want to point out, so here we won't be able to prove the control guarantee, the FDR control guarantee for the method where we tune to target FDR. Okay, so how do we actually come up with this estimator? So I'll just introduce sort of a generic parametric setting. We observe some data set, generic kind of data set from a distribution with some parameter theta, and we'll just assume it's a d-dimensional parameter. It's not really important that this is coming from any kind of parametric model at all. There doesn't need to be any kind of d-dimensional parameter in the problem, but just for concreteness when we're introducing the method. So we have some parameter setting, and we have some maybe sparse estimator data hack. So there's some notion of variables that are selected and variables that are not selected. And so then we can define the false discovery rate if we think of a variable being selected as being like a rejection of a null hypothesis. Then the natural definition of the false discovery rate would be the number of zero variables that are estimated to be non-zero, or the number of selected variables that are just noise variables, divided by the total number of selected variables. At least that fraction is the false discovery proportion, and then the false discovery rate is the expectation of that. So that's what we mean by false discovery rate in the talk. Okay, so now we might have a particular estimator theta hat in mind, or we might have some path of estimator theta hat lambda. we might have a path of estimators, according to some tuning parameter, and then maybe we want to estimate the false discovery rate for each. That is boiled down by doing the same procedure for each one. Okay, so the key statistical assumptions here to be able to estimate the false discovery rate is going to be for each of the hypotheses. Each of the null hypotheses, we have some sufficient statistic that we're going to call S sub j. It doesn't mean that there's a vector S and this is the j coordinate of that vector. I don't want to that. It's just for each hypothesis, I have some sufficient statistic for the null hypothesis for that parameter is equal to 0. For that submodel. And as long as I have that, it allows me to make a lot of computations. Okay, so two key ideas. One is round black-milization, and the second is the decomposition of the false discovery rate into the contribution of each variable. So I'll talk about the second one. I'll talk about those two in turn. Okay, so what do I mean by a sufficient statistic Sj for the null submodel? Okay, so again, let's just make this concrete. So suppose that I have a linear model. The statistical study we're working in right now, say, is a linear model with fixed design. And if I have some non-singular, feature matrix X, which is just fixed. And I assume that I observe X theta plus some Gaussian errors with unknown error variance. The sufficient statistic, there's a complete sufficient statistic for this model, which is X transpose Y and the total 2 norm squared of Y. You can directly read this off of the exponential family form, that this is a complete sufficient statistic. Again, X is fixed, so X transpose X is not really a statistic. This is a complete sufficient statistic for the model, or equivalently, I could replace this with the residual sum of squares. It would be the same information. Okay, so that's for the full model. For the submodel, where I assume that theta j is equal to 0, I have a sufficient statistic with one less dimension. So it's just the same statistic, but for the model with that variable left out. And so this is the Sj that I'll be talking about. And under the null hypothesis, under Hj, we know that Y is the conditional distribution given Sj is uniform on a sphere of dimension n minus. Okay, so this conditional uniform distribution is what we're implicitly appealing to when we perform CPAP. So, for example, we know that the distribution of Xj transpose Y, conditional on that sufficient statistic, is given by some transformation of the statistic. But in particular, we also know, again, under the null model, conditional on the sufficient statistic, we also know the distribution of the estimator. We know the distribution of anything. Again, it's because that follows from the fact that this is the null model. Any questions about this? Okay, so it's very important. The null sufficient statistics, they allow us to, once we condition on those, then we can do any kind of computation that we want under the corresponding null. Okay, so we assume that we have a sufficient statistic for these submodels. But this framework, okay, so this framework is really sort of the master key for all kinds of fine example hypothesis testing and inference. So for example, so essentially what it does is it blocks the influence of distance parameters. So it's a general recipe for UMPU testing. and many non-parametric and non-parametric settings, how we construct tests to test each J. So, for example, statistics, Gaussian linear model, but also there's Gaussian graphical model, Fisher exact test. These are parametric examples that you can sort of do with any kind of exponential family, but also you have permutation. So permutation test can be viewed as a version of having a null sufficient statistic and conditioning on it, where the null sufficient statistic for a two-sample permutation test is just a pooled empirical distribution. Okay, so again, this assumption that we have these null sufficient statistics is really our main statistical assumption. Okay, so now we get to the key ideas in constructing our estimator. The first is the notion of FDR decomposition. So the first thing that we're going to do to estimate the FDR is we're going to break the FDR into the contribution, to the FDR contribution for each variable individually. So here we're really just using linearity of expectation. So if I write the false discovery rate as the expectation of this fraction, the first thing I can do is, so this is just the number of variables in this set, but I can turn this into a sum of indicators. So for each j, I have an indicator that that theta j is 0, but that it was selected by the model. And then I can just turn this into a sum and pull the sum out. Then I can pull the sum out of the expectation as well. When I pull the sum out of the expectation, I can also turn this indicator into a product of indicators and pull that out as well. And so the key part that depends on the data for each term is the expectation of just the indicator that theta hat that theta j is selected, variable j is selected, divided by the number of rejections. So I'm going to call this the FDR 0 of j. This is the FDR contribution, of variable j if it's null. And there's only a contribution if j is null. If j is non-null, then it doesn't contribute anything to the false discovery rate. Okay. So we're going to try to estimate this red term. The FDR contribution of the jth variable is this quantity, we'll define as this quantity times this indicator. And now we've reduced the problem of trying to estimate the false discovery rate overall to the problem of trying to estimate each of these terms. Okay, so that's idea number one. Idea number two is how are we going to estimate each term? Okay, so the way that we estimate the false discovery rate contribution for each term is, so again, we assume that we have some sufficient statistic for the null submodel. We condition on it, and then we estimate this, which is just an expectation. We estimate it by Rao-Black localization. So we can get an unbiased estimator for this red term by conditioning on a sufficient statistic for the null, and then just calculate its conditional expectation. Now, something important to note here is up here, I'm just, this expectation is supposed to be taken over theta. So in general, everything about this is going to depend on theta. It depends not only on theta j, but it depends on all the other thetas. Right, so if beta j is 0.1, that's not going to tell me all by itself. That doesn't tell me how likely variable j is selected. Or it certainly doesn't tell me how many variables are going to be selected, the distribution of that. That would depend on all of the other thetas. But once I condition on Sj, it doesn't depend on the other thetas anymore. And so I can actually just calculate this either by Monte Carlo simulation or by a one-dimensional integral conditional on Sj. Okay, so as an estimator for FDRJ, it's so this again. This is just Rao-Black localization, and so if the null really is true, then then I'm calculating the right conditional expectation here. And so then this is unbiased for the thing that I want to estimate. Well, okay. But I'm calculating this conditional expectation under the null, but the null might not be true. But that's okay, because if the null isn't true, then if the null isn't true, then this indicator is 0 anyway. So all I need to be able to say, and all I can say, if theta j is non-zero, is that this conditional expectation is going to be non-negative. So if this term really is null, then this is unbiased. An unbiased estimator for the term. And if this term is a non-null term, then this is positively biased, because the thing I should be estimating, the estimand is 0, and the estimator is always non-negative. Okay. So again, to remember, so maybe one thing that's worth just sort of thinking about here. If we assume that we're in a large problem, so that once I condition on Sj, again, this is conditioning on the correlations of all the other variables. So here, when I condition on this, I'm conditioning on quite a lot. So this, the size of the model might be, you can think of it as being fairly common. But once I know the correlations of all the other variables, maybe I know there's going to be about 50 selections. And so then what this expectation becomes is roughly the probability of the variable being, the null probability of the variable being selected in this particular context is determined by all the other variables correlation. But that null probability of being selected divided by the number of rejections. So that's roughly what this is going to be. Okay. Okay, so now we're almost done. So I said we broke it into these terms, and we just want to get an unbiased estimator or conservatively biased estimator for each term, and we're basically done. So here again, this estimator that we defined formerly, that we defined on the last slide, we know that if we were just able to sum over the terms where it's null, we would have an unbiased estimator for the FDR. But we don't know which terms are null, and so we're going to have a positive bias coming from the other terms. And this positive bias actually could be quite large, because for the non-null terms, first of all, we're calculating the conditional expectation. So we don't really know, we're conditioning the conditional expectation under the wrong value of theta j, so we don't know what it looks like. And furthermore, the probability of being selected might actually be pretty high for various reasons. So this positive bias can actually be quite large here. And so we want to do something about this positive bias. Essentially, we want to kill the terms for which the hypothesis is demonstrably non-null. And so that brings us to our idea of bias reduction. So instead of just stopping at this estimator, to estimate this term, we're going to multiply it by something that has expectation 1 under the null, and hopefully expectation close to 0 under the alternative. So we're going to have this psi j, we want it to be 0 with high probability. If theta j is demonstrably non-null, we want to be able to kill this term with high probability. And if we don't kill the term, then we know that we might have killed it, and so we have to basically divide by something so that we lose it. I'll give you an example. So a simple example for what we're doing here is we could take this psi j to just be, so I'm sorry, this should be the indicator that pj is larger than 1/2, not smaller than 1/2. So again, for a non-null, pj should be small. So this, again, pj is some p-value for variable j. So for a non-null, it's going to be small most of the time. And so we're going to kill the terms for which it's small. So again, I apologize, this should be greater than, not less than. So we kill all the terms whose p-values are below 1/2. And the terms whose p-values are above 1/2, even under the null, there was a 1/2 chance that the p-value would be below half. And so we have to multiply, we have to double the other terms so that we don't bias the estimator. Okay. So again, we want to kill most of the non-null terms and adjust the null terms so that we don't lose anything. Okay, so the generic formula, if we have some, I'm sorry, I'll come back to this. Well, okay, so that was example number 1 with the p-value being bigger than 1/2. And then example number 2, if we're doing something like a lasso, where we have now theta hat lambda, then we might take some relatively liberal value of lambda, let's say lambda 0. So lambda 0 might be like some estimate of the residual variance. So we expect that, if we were to actually run lasso at sigma, then we would expect, some reasonably large fraction, maybe 30% of the nulls to enter the model, and most of the non-nulls would be entered the model. And so we just say we kill every term that ever enters the model for any value of lambda that's larger than lambda 0. And so the terms that aren't killed, are the terms for which the variable never entered the model. And the terms that never enter the model, it's actually easier to do this integral calculation. So this can also be a convenient form. Okay, so bringing it together. So this is our FDR, and we turn it into this. We decompose it here, and then our estimator. So again, we take this quantity, which is an unbiased estimator itself, and then we take this quantity, which is a bias reduction. And again, this Sj, all we have to assume is that we have some sufficient statistic here. And now I claim that any estimator of this form, we take any psi j here without really any assumptions about theta hat, that this FDR estimator is always conservatively biased, regardless of the theta. Okay, so why is this? Well, let's examine. So it's sufficient to prove that each of the terms is conservatively biased. So again, when theta j is equal to 0, this expectation conditional on Sj is this term, which depends only on Sj, times this term, whose conditional expectation is 1 given Sj. So that's for the nulls, and again, for the non-nulls, there's nothing to do. And so we always have this conservative bias. So that's with parameters, but again, I told you it doesn't really have to. This is not really a story about parametric models. So we might just have generic submodels. So for example, if you're familiar with model X knockoffs, that's something where we might have a very high dimensional regression with many more variables than we have data points. But what is assumed is that we know the distribution of X, of the entire vector X. So if we know the distribution of the entire vector X, is something you can do on a conditional randomization test where we can still get a legitimate p-value. And so then there's still this Sj that we can find. But yeah, so just generally speaking, as long as we have some sufficient statistic for any generic submodel, then we can just replace what we had here, and mutatis mutandis, we still have the same proof with. Okay, so just to get a little bit more concrete about the implementation. So for the lasso, what do we actually do? So this beta hat lambda, it's a function of x transpose x and x transpose y. So what we're doing is we don't actually need, so when we calculate this conditional expectation, we don't actually need to sort of regenerate the full vector of y. We don't need, we could do a Monte Carlo sample where we condition on the sufficient statistic and generate full data sets and then recalculate the whole lasso. But we don't actually need to do that. So instead, so we're conditioning, so this is just fixed. And then we're going to condition on x minus j transpose y. So that's also fixed in this calculation. And so we're going to hold that fixed. And then we're just going to change what xj transpose y is. And so we're going to vary xj transpose y, and that's going to vary the lasso beta hat. So again, think of this as just for a single lambda. We're doing this for one single lambda. So we're just going to vary y in one single direction, holding the correlations with the other variables there. Okay, but the distribution of this quantity, this last direction about y that we need to integrate over, it's just actually a very simple transform, a nonlinear transform, but a very simple transform of the t statistic. So we could just generate t, or we could integrate this t against the t distribution, and sort of plug it in here, and we can use a homotopy algorithm to trace out with the lasso solution of its full one-dimensional subspaces. Okay, so these A, B, and C are just constants once we position on SJ. Okay, so one thing I want to bring up is, again, this conditional expectation. You might worry about, we've made these parametric assumptions. How strongly are we relying on these parametric assumptions? So essentially, we're relying on the parametric assumptions to the extent. So this entire calculation can be done just as a function of this t statistic. So as long as this t, so if the parametric assumptions don't quite hold, but this t statistic that we're integrating against is still approximately t distributed, then the conditional expectation is fine. So here again, so this, because this is just a simple function of the t statistic, actually this whole quantity is a bounded function, a bounded piecewise constant function of the t statistic. And so this conditional expectation says a conditional expectation of a bounded piecewise constant function of the t statistic. So as long as the t statistic is approximately t distributed, then we should be getting approximately the right answer here. Okay. So continuing on for the lasso, usually what we use is, again, take some liberal value minus 0, which is probably smaller than all the values of lambda that we care about. And then we add these variables are better 0. And any variable that ever came into the model, we think that might be a non-null, so we're going to kill it as part of our bias reduction strategy. And we're going to take the variables that are always inactive, and when we're integrating against them, actually this also makes the calculation much simpler. Okay. So next, forward stepwise. So that's for lasso. But again, I said there's not really anything very special about lasso here. We can do the same thing for forward stepwise and very little changes. So the lambda becomes a k because that's the tuning parameter for forward stepwise. But we have actually the same sufficient statistic. The statistical structure of the model doesn't depend on forward stepwise versus lasso. And then we can, instead of using a liberal lambda 0, we could use a liberal k0 or something. And the calculation remains very much the same. It's just this integrand is different. It's just a different piecewise constant function of the t statistic. But we could also do this for group lasso. So we could have group-wise null hypotheses that, again, if we were testing a single one of them, now we would test it via the F test. So the sufficient statistic for the null is now we drop all of those variables out of the model and take the correlations to the other variables with y. That's our new sufficient statistic. And again, so we can do this for group lasso as well for these group Wise hypotheses. Lasso under the model X knockoffs assumptions. Again, if you're familiar with model X knockoffs, the corresponding sufficient statistic for a conditional randomization test is all of the variables except for J, not just X minus J transpose Y, but X minus J itself and Y. And then the way a conditional randomization test works, we're testing whether Xj is conditionally independent of Y, given X minus J. And so we can just simulate new values of Xj that are conditionally independent of Y under their known conditional distribution given X minus J. So again, that's a conditional randomization test. This is the correct sufficient statistic, and we can just do this. We can do elastic net, SCAD, graphical lasso, and so on. Okay. So now we're going to examples. Okay, so first, so here this is lasso and the Gaussian linear model. I'll show you some simulations. So here we have 3,000 data points, 1,000 variables, 15 unknown. And we try various different choices for the design matrix, either the MCC, the sort of blockwise equicorrelated version that I was showing you before, or IID normal, AR process, or these should be beta hat 1 through beta hat D have an AR structure. So this is saying that the X transpose X matrix has like an AR covariance, AR 0.8 covariance matrix. And this would be saying that X transpose X inverse has the same structure. Okay, so then for all of these, we calibrate the signal strength so that the BH procedure has pretty good power. The BH procedure at a fairly liberal 0.2 level has pretty good power. Okay. So here, so we see that first of all, this is a function of lambda. So here the lambda is larger, we have less. This is a function of lambda. What I'm plotting here is the false discovery proportion, and the solid red line is the expectation. Right, the solid black line is the expectation of the false discovery proportion, which is the XR. And I'm also showing you the standard error in deviation. And then the solid red line is the expectation of our and the red of ours is standard deviation. So one thing to note is that we don't have very much bias in this case. So again, we're doing a good job of killing most of the non-null terms most of the time. And then secondly, one maybe interesting thing from this plot is that our estimator for the false discovery rate seems to have actually a smaller standard deviation than the false discovery proportion itself. So we're doing a better job of estimating the false discovery rate than we are of estimating the false discovery proportion. And this curve is the power. No, this curve is the true pot. This curve is the I think 1 minus the power, I believe. Okay, so and the same story basically is true for the different versions of the design matrix. So that's for the lasso. For model X assumptions, we see similar things happening, maybe a little bit more bias here, but still not too much. We can also, again, do this for the graphical lasso. So here we have 50 variables and 2,500 samples, 50 active edges. So again, we're calibrating a moderate signal strength in the same sense. And now for the graphical lasso, again, the statistical model here is the Gaussian graphical model. And the complete sufficient statistic for the submodel with a precision, with this edge of the precision matrix set to 0, or this entry of the precision matrix set to 0, the complete sufficient statistic is basically everything else, the covariance matrix. all the other entries to the variance. So that's our sufficient statistic. And the test statistic that this is built on for each part, that again is statistic. Okay, so again here, the method is working pretty well, fairly low bias and fairly good error rates. Okay, so for a real data example, we go back to the graphical lasso example from Sachs et al. Sachs et al. Was this is the example that was used in the original graphical lasso paper. So here, Sachs et al. They were estimating protein signal networks, 11 proteins, and they had single cell flow cytometry data. And then they had a bunch of different experiments where they perturbed the cellular systems in various different ways, 9 different ways, and they analyzed how the correlation is. And they were looking for the causal graph for how these proteins related to each other. So this example was the illustrating example in the graphical lasso paper. What they found is that the best cross-validation error was on putting everything in the full graph. So this doesn't really tell us which graph to actually choose. So they just showed a range. They showed a range of graphs, but they said we don't really know which one to choose. If you use cross-validation error, the data set is large enough that it'll just tell you to do the full graph. But what does that really mean? And again, for something like the graphical lasso, we would expect that the cross-validated lambda would overselect if we're thinking about type 1 error. Okay, so Sachs et al. They had 9 different experiments, and they combined their knowledge of biological theory with the results of these 9 different experiments, and they found what they believed was a 19-edged causal graph. And so we take that causal graph and we moralize it to get an undirected graph. And then we use that as our ground truth to estimate the FDL. Okay. So here, just analyzing the data from experiment 1. So again, we see that the cross-validation error is minimized when lambda is smallest. So this doesn't really tell us that much. But if we can actually estimate the false discovery rate, then that actually is showing us that there's a transition that's happening. So when lambda is very large, we have almost no false rejections. And then there's a transition from a fairly low false discovery rate to a fairly high false discovery rate. If we compare that to the actual FDP, according to our ground truth, then it looks like at least we did a reasonable job of figuring out where this transition occurred. And so the model that we got over here seems like the edges are highly trustworthy. Over here, not so much. And here it's kind of in between. Yeah, so I would argue that if this cross-validation curve was all that we had to go on, we would definitely be happy to have this just as additional context, even if we're not necessarily going to use it in a formulaic way to select the model. Okay, so this was the Sachs graph, and this is the graph. If we choose the biggest model with false discovery rate estimated at 10, we get about half of the edges in this graph. We got more of the short ones than the long ones, so it looks like most of them are missing, but we got about half the edges in the graph and 1 false discovery here. Okay, so next I want to talk a little bit more sort of philosophically about whether whether we should really be interested in false discovery rate control or false discovery rate. So as I told you before, so this method, compared to other false discovery rate controlling methods, it has a lot of benefits, right? So if we compare to a method like the pH procedure that is not really able to use sort of a variety of estimators, it's just looking at p-values. Or we could use something like knockoffs. Knockoffs has some of its own issues if you're familiar with this method. For example, it starts off by injecting all these variables into the problem. and then it has a sort of highly discrete estimator of the false discovery rate that can be highly biased. We may not be able to make very projections, if particularly in smaller problems. So there are reasons why we might not want to do knockoffs, and there are also problems like the Gaussian graphical model, like the graphical lasso, where there isn't really a way to control FDR. And so what we gain by moving to this approach is that we have a much more general framework under which, for a sort of general estimator like the lasso or stepwise that may be attractive to us for some reason that doesn't have to do with multiple testing. But we cannot prove FDR control for this approach. So we've lost the sort of provable FDR control, and but we've gained generality. Okay. So we might say, sort of natural idea, maybe it would just work. Say, well, we'll just choose lambda to be the most liberal value, such that the estimator of the false discovery rate is less than or equal to alpha. And again, we don't prove, we don't have a proof that it actually controls FDR. But empirically, this works reasonably well. So if we compare, so in this problem, we have 100 variables, 10 non-nulls, IID Gaussian design. So if we compare our method to a variety of other methods like knockoffs, this problem is a little bit too small for knockoffs. The BH method is hiding under this blue curve, has decent power, but not very good. And the lasso is doing substantially better here, because the lasso is actually able to exploit the correlations, the correlation structure between the t-statistics that the BH method can't. So it's getting higher power, and the FDR, it's actually just about right. The FDR is lined up pretty close to the actual advertised FDR. We generalize this to the other design matrices, and for the most part, it seems to be controlling FDR, although over here, it seems like we're exceeding FDR. So again, there's no guarantee here, but it seems to work fairly well. Okay. But what if we actually want provable FDR? Okay, so one idea is to use this method as a baseline for conditional calibration, which is a sort of more general method, or a method for getting FDR control under default leg with the same collaborators for the last couple of years. And so I think that this approach could work, but the method that we would get out is much more complicated, more computationally expensive. So I'm not really sure that it's worth it. Another idea would be to stick with the simple method that we have and try to do control in large problems. I believe that in large problems, we should have asymptotic control. Empirically, it seems to be true. Currently, we can only show this under fairly restrictive assumptions, namely that we'd have sort of independent blocks. But if instead of independent blocks let's say that you have orthogonal blocks in the design matrix, then we can prove asymptotic control. But the moment you go from orthogonal blocks to sort of a banded X matrix, you would think you could still prove asymptotic control. I think that you still have asymptotic control, but it's just hard to prove. And it's just generally, it's just kind of hard to control this component, because a method like the lasso, and certainly a more general, if we want to prove things for a general method, there can be long-range dependencies between which variables come into the model, even if there are not long-range dependencies between the corresponding t-statistics set. Well, when I say there can be long range, probably there can't, but it's harder to show that there can't be, because the lasso is using all the variables in a complicated way. Okay, but I'm interested in question of FDR control, and I spent a lot of time trying to prove FDR control in a lot of contexts. So I like to think that at least sometimes FDR control is the right goal, but I don't think that it's always the right goal. So, so one thing that I think we multiple testing folks don't always emphasize enough is that model selection and multiple testing are really not the same problem. So to kind of try to illustrate this as clearly as possible, consider the following example. Suppose that I have two variables, a model with only two variables, or not a model, I have a regression problem with exactly two variables. The F statistic for both variables might be extremely significant. But if the variables are highly correlated, it could be that neither T statistic is significant, even though the F statistic is highly significant. If we think about this from a multiple testing perspective, we really cannot establish with confidence that either of these variables has a non-zero coefficient. And so the only, if we wanted to have any chance of FDR control, then the only method that could have a chance of FDR control less than 50% would be not to reject either variable. But if we care about is model selection, choosing neither variable, that's the only bad choice. It's the worst possible choice, right? So what we know for sure is that one of these variables ought to be in the model. We're not sure which one, but probably fine to put them both in, or pick arbitrarily between them. Either way, that's going to give us, the F statistic tells us this is going to give us a much better model than if we don't take either variable. And so again, the choice that we would be forced to choose if we were doing multiple testing with FDR control is the only wrong answer in the model selection problem. So again, depending on the structure of the problem, in a regression problem especially, but in other problems, well, depending on the structure of the problem, it may be inappropriate to focus too much on type 1 error, because in model selection, type 2 error can matter a lot. So just insisting that we're going to have a false discovery rate of 10%, there might be certain problems where what we really care about is the discoveries at a accept reject level. But for a generic situation where we're running the lasso or a graphical lasso, it's not the only thing that we care about. So if I can get a model that explains the data much, much better, but the cost is that my false discovery rate goes up from 10% to 20%, I'll probably accept that. And it wouldn't be appropriate to insist on, no, I said it has to be 10%. Yeah. So, so depending on the goals of the problem, we need to trade off type 1 error and type 2 error. We need to trade off model fit, the parsimony of the fit, and so on. So again, if we were going to tune lasso, I'm not sure that I would say that we should pick, even if we knew the FDR, even if we didn't have to estimate the FDR, we actually knew the FDR. I wouldn't necessarily say that we should choose the most liberal lambda with FDR less than or equal to 10%. Actually, it can go the other way too. Just as we might, just as by insisting that FDR is less than 10%, we might underselect. Likewise, it could be that the model with best cross-validation performance has an estimated FDR of 5%. Should we make the model even more liberal just to push the FDR 10%? I would say no. For losing predictive performance and increasing the FDR, I would rather have a model with better predictive performance and lower FDR. Okay. So, yeah. So it could be the FDR model, but the model with FDR really higher than we asked for, and much better fit, or it could be the cross-validation has a low FDR. Okay. So again, I think in a more general model selection context, it's more appropriate to use the false discovery rate to the extent that we can, estimate it, is to use the false discovery rate potentially to be an input into guiding the model selection, or certainly to evaluate the model that we end up selecting, but not necessarily to determine model selection. Okay. All right, so to summarize again, so we have a general purpose estimator of SPR, which includes the purposely bias. The core thing that we need is to have a sufficient statistic for each null hypothesis. A sufficient statistic for each null hypothesis already exists in many hypothesis testing settings. So we're just sort of reusing the statistical structure that we were already relying on to do a single test. And we have some estimator, quote unquote, estimator of the indicator that they so we can do this for lasso, elastic net, forward stepwise regression, and a variety of other models. So again, use cases, I think, interpretability. So we might just assess the model selection reliability of a fixed estimator that we were already planning to use. We could use it as informal tuning as a companion to cross-validation of Stein's unbiased risk estimator. Or we could use it as in an informal way to do multiple testing to get approximate FDR control. Okay, so thank you very much.
Any questions?
Thanks much for Dennis for the interesting product. My question was, so you talked about how this procedure requires that you have would you be able to say a little more about like what exactly the requirement is? Is it the existence of the distribution that I mentioned? Is it that this individual distribution is that pipeline is practical? Like, what's it?
Okay, so that's a good question. So what actually do we need about this sufficient statistic? So to show that this expectation is actually larger than the FDR, then we just need existence. Now you might say, well, wait a second, you could just use the sufficient statistic for the full model, so then this becomes back. And that's true. Then we would just have a very bad estimator, because we would be conditioning, then we would be conditioning on a sufficient statistic for the full model, which is probably the same conditioning on the estimator, so we could calculate something. That wouldn't really make sense. So it's we want something like a sufficient statistic for the null model that is nowhere close to being sufficient for the full model under the non model. Okay, so that's so we really just need it to be sufficient for computational reasons. I wouldn't say that we want a sufficient statistic to be low dimensional. It would be actually preferable probably for the sort of remaining part of the sufficient statistic. Like if the sufficient statistic for the null is x minus j transpose y, that's b minus 1 for them. And then the remaining part of the sufficient statistic that I have to integrate over that low. That's actually, I would rather have that because I'm now doing a one-dimensional integral. So probably ideal, it would be ideal that we have one fewer and typical that it would have one fewer dimension than the sufficient statistic for the full model.
Thank you. I think that also answers my second question, which was physics how reduced other than that. Have you looked at how the performance of your bias varies with like how good your statistic is?
That's okay. That's an interesting question. So if we didn't have a minimal statistic, so statistically, I think we would want a minimal sufficient statistic for the null. But if there weren't one, how would we choose between it? I'm not sure. I don't have a good. I don't have a good play example in my head. But we have a minimal sufficient statistic. Now, maybe the question is why would we want to use the minimal sufficient statistic? I have a strong intuition that we would want to use the minimal sufficient statistic for hypothesis testing. Usually you want to use a minimal sufficient statistic. You want to condition on a minimal sufficient statistic of null, so that you have the most difference in the conditional distribution of null. So if you conditioned on the entire data set, that's it. But then the null and the alternative merge. So typically we want to condition on minimal null, so the conditional distribution is very different than the alternative. My intuition is that that would be give you probably better bias variance for our estimate here as well. But I'm not sure exactly about. But it's very
Any other questions? If not, then I think we're over time, so let's thank Will again.
okay. Thank you very much.